In this chapter, let's focus on how do I do exponential smoothing if my data is having a trend. Just with a mere observation, I am able to see that this particular data, which is in the B column, is exhibiting some level of trend. Overall, there is a kind of uppish move in the data. Let me just simply look at a quick chart. Somewhere it is showing that there is an upward movement, and even if I am trying to plot a trend line for it, it is showing that there is some level of upward movement in the data. Okay, that's my first level understanding, that this data has an upward trend. If the data is having an upward or a downward trend, not a flat trend, or flat trend is as good as not having any trend. If my data is having a flat trend or a horizontal trend, what we have to, we can use a direct exponential moving average itself. But in case it is having an upward or a downward trend, the concept that is first used is, there are two things which we'll discuss as a part of this chapter. One is a first differencing mechanism, where I create the differences, and based on the differences I'll try to create the forecast. So that kind of mechanism is what I call as a first differencing mechanism. Then I also use Holt's linear exponential smoothing mechanism, so named after a guy called Holt. Exponential smoothing, linear exponential smoothing mechanism. So these are the two methods we'll try to use, especially though there could be a couple of other methods which we'll deal with as we move along. But in this chapter, we'll try to look at these two methods, especially applicable for forecasting a time series data which has a trend in it. Now, the way I proceed, the first column I'll take as first differences, which is nothing but the difference between the second value minus the first value. So I am simply taking the first differences as the difference between the second value minus the first value. Alright, so it is coming out as minus 37.83, and when I am dragging it down, these are the differences that have come out. So this is what I call as the first differences. So now what we observe is, when I try to plot the chart of the first differences, it is assumed that this particular first differences do not show much of a trend. If required, plot a chart and also put a trend line. What we could see is more or less a flatter, slightly, right? So this is it is assumed that if I am doing a first difference, the trending is actually going off. So in one period, if the value is up, the second period the value is down, and so on. So there is no scope of too much of an upward trend or a downward trend. But it is very much possible that even after the first difference, in some of the examples, the uptrend could still continue. Then we may end up doing a second difference or even a third difference in those kind of data. Now what we'll do is, on the differences, we'll apply the exponential smoothing mechanism, which we have done earlier. Then, so what we are doing is, I'll take one more column called forecast differences, which is more similar to whatever the differences which we are trying to bring out from the earlier period, which we have done earlier also. For the first period, the differences will be as it is of the previous period, but we'll take the forecasting error, and so the differences error is what we'll take. which comes out as the actual difference minus our forecasted difference. And from the next period onwards, I'll adjust the forecast difference in such a way that I take okay, now I have to put one decay factor or smoothening constant. Alright, so I call smoothening factor and give some value, let's say as 0.1. So this is the 10% weightage which I would be giving to the difference in the forecasting error, or difference in the error, or the first difference is whatever is the error between the actual first difference and the forecasted first difference. So what I would simply try doing here is I'll take the previous forecast plus 0.1 times. So this which means I'm adjusting the forecasted difference. So wherein I am taking this number 0.1 times the previous error. So I am trying to adjust the difference in the upward direction to take care of the positive error that has come earlier. Now this resulted in even more positive of 64, which I have to take care of in my next observation. So that is how I am proceeding further. So this is what is updating my numbers, saying these are my differences in the errors, and because of which these are my updated forecasting differences. Now the forecast differences are updated. The first differences are this. These are my forecast differences, and based on that I'll go with the integrated series. So my next intention is go with the integrated series, wherein what I'll simply take is, for the first period I'll take the value as it is. The integrated series for the first period I will take it as it is, but from the second period onwards I can very well revise my numbers corresponding to the next period. What I could very well do is I'll take this period and add up the forecasting differences of this period. So my number is going to show up 206 here, and the same way I can proceed further. So this one also I could have very well taken, instead of V2 I could have taken added up the forecasted difference. So this is also giving me, so these are my predicted numbers, and I can very well use the standard error, which is again going with the sum of the squares method. So I'll take the standard error in the estimation process using the sum xmy2 process, wherein the array 1 is my original numbers and array 2 happens to be my integrated series. So these are the two numbers, and of course I should divide this by the count of these total numbers which are getting forecasted. Alright, and a square root on the top of that. So this process does not change whether I am using the with a trend or without the trend. The only difference in this case, if I had directly done this forecasting without knowing that there is a trend, my number could be completely different. Whereas if I am doing it with this method, my numbers with respect to my forecast are much more different. So what I am ending up with is, with the first difference mechanism, that these are the numbers, and probably if required I can do the forecasting for the next period, which should give me, for the next period, the forecasting is telling me that the value will be 803.82 itself. right? Even if I am taking this or even taking this, yeah, it says that this number could be 793.67 because these are actual values. So we cannot have much of a thing on these. So that's where I'm looking at having the previous actual values and then modifying it based on which it ends up as 793.64 being our next period forecast. Now what I have to do is to make sure that my numbers are much better. I have to find out what is the appropriate value of the smoothening factor so that my standard error is as much minimum as possible. Again, I can use solver in this case, right? So for the solver, all I am taking is the target cell, which is the standard error. I'll set it to minimum by changing the smoothening factor value. And of course, I have to add a couple of new constraints. And the constraints for me in this case are the smoothening factor should be less than or equal to 1, as well as the smoothening factor should be greater than or equal to 0. Alright, so we are adding these two, and based on that, asking the solver to actually resolve this question for us. And that is saying that in this case, take the smoothening factor as 0.056, which is 5.6%, and that is giving me the forecast as 799.85 for the next period rather than 803, which was there earlier when we have taken a smoothening factor of 0.1. So so this is more applicable in case there is a trend. What you are seeing in this case is even though the data has gone up or gone down, the moving average form plays a very important role in terms of understanding the movement in the pattern. So just to summarize what we have done here, the first thing we have done is we know that the data is having a trend in it, which we have got by plotting the data series. The moment we know that we have a trend, the first mechanism which I am trying to observe is find first differences. And the first difference mechanism is nothing but you take the difference between the current value minus the previous value as it is and take the numbers. Now, ignore your original data. On the first differences, do an exponential smoothening. So from C column, taking the C column as the actual input data, what you have to do is you start doing the forecasting. What is the way we have done for smoothening out the data using an exponential mechanism? The first value, I'll take it as it is of my original data. Then I'll compare what is the forecasting error, because I am forecasting it as the original value itself, but in reality the difference has come out to minus 9.27. So the difference between the two ends up as my error. Now I am modifying my forecast for the next period by incorporating this improvement that has come between the actual value and the forecasted value. So based on that, what I am saying is, and for next period, I will not consider minus 37.83 as my error. Rather than that, I will, as my forecasted forecast value of the differences, I'll enhance this number by giving some weightage even to this difference. So when I'm saying I'm giving a weightage to this difference for the next period, I'm reducing this difference as minus 36.21. But in reality, the difference has come out to 29.21, which has again created that actually there is a rise, whereas we are considering it as a fall. So that what should again go back into our forecasting mechanism. So the 65, the 10 or some percentage weightage I'll give to this 65 and add it back to minus 36. That's what will become the forecasting the difference between the difference for the next period. and the same thing, but the actual was 6 points, so the difference came the difference between the actual as well as the forecasted value has come out to 39. Now that's how I'm coming across. Now this process will keep on continuing, and that is what is telling me that 3.96 is the forecasting difference for me, whereas what we are forecasting for the next period is a drop of 3.96 compared to the previous value. So we know what was the previous value. A drop of 3.96 is actually giving me a number 799.85 in this case. So using the first differencing method, all I can say is for this kind of a data series, 799.85 appears to be the value for the next quarter based on the first differencing method. Right? Now, if I have to use another method, which is the Holt linear smoothening method, in this case, what is the process I would be following? There's a slight difference. So what I'll do is I'll open up a new sheet, and in this sheet I'll call it as Holt method, especially again applicable for your time series data only. I'll just take only these two columns of data to start with, the date as well as the share price. Now here I will mention the Holt method actually goes with the two parameters. Right? We'll discuss them as we keep using them. The Holt method goes with two parameters. One is called as a level parameter and the other one is called as a slope parameter. How do I define these two things? So it tries to understand what is the current level of the data as well as the current slope of the data. Now, the current level is typically the current level which I use it is based on the trend. I'll come to it. Whereas the current slope, I'll see at what rate, what is the difference in the level from this period to the next period. So it looks at if at all there is a level thing, if at all there is a level stuff, what should be the value, and if at all there is an improvement compared to the previous value. So it is more applicable to our kind of a data, because even after taking the first differences, what we have observed is there is a kind of downward trend in our data. So it will observe if it has been level, what would have been our numbers, which is more similar to our first differencing method. But if something is not level, what is the slope factor associated with it? That is what is being taken care of by our Holt smoothening approach. Now in this, as I said, I will be using the level as well as the slope. So based on this, let's see what is my forecast number, forecasted price in my example, then forecast error. Right, I'll use the forecast error, more similar to any other method also. So I'm taking the forecast number as well as forecast error. But here we have to understand there are two constants that are being looked at. One constant is associated as the coefficient to the level parameter. The other constant is the gamma, which is associated to the slope parameter. So our actual forecast will come out as the share price plus previous share price plus something times the level parameter, alpha times the level parameter plus gamma times the slope parameter. So instead of just looking at it as the flat value which was looked at by our exponential, the other exponential smoothening method, the Holt linear smoothening will take care of both the level as well as the incremental part. Now, just to go ahead with it, in the forecast part, I'll take the value as it is for the first one. I'll take the value as it is which I have taken for the first one, and or let me do one thing. The level estimate is assuming there is no upward trend or downward trend. So what I'll do is, for the first month I'll take the level estimate as the same and the slope estimate as 0, because it does not, I'm making an assumption that it does not either move up or move down. So because of that, my next period forecast is actually coming out as the level estimate plus the slope estimate of the previous period, which is ending up with 282.61. And what generally happens is I can drag this down, because depending on the level estimate as well as the slope estimate of the previous periods, I'll get my forecasted values. Now, as we are saying, how do I compute my level estimate? So here the level estimate is typically coming out as, now there is a forecasting error here, because I am estimated it as 282.61. There is a forecasting error, which is the actual value was 244.78 minus the forecasted value was 282. So there was a forecasting error of 37. So this is one thing that is coming out. Now what we are saying is, I'll give some kind of a weightage to the forecasting error, right? The forecast error compared to the previous period, and this is the forecasting error. So I have to give some kind of a weightage to this forecasting error, and needs to take care of the updated value. Alright. Now, as I need to consider my forecasting error and reflect it into my next period's value, what I can do is I'll calculate the level value now for B2, because if there has been no increase or no decrease, I could have immediately taken care of this part itself. Now, let's say, because there is a difference of 37.83, my next value for the level should take care of even this difference. So what is the new difference that I have to come out with? The new forecast for me is the previous value plus whatever is the alpha time. So let me take alpha as 0.1, which is associated with the slope parameter. So I'll take my new calculation has to, my new forecast has to be upgraded based on the forecast error. So I'll take this number plus alpha times the forecast error, which is resulting in 278.827. So based on this, it's as good as. Now how do I arrive at this 278.82? The other way of handling this 278.82 for me is, the other way of handling this 278.82 is nothing but you do it as alpha times the share price, which is the original, which is the actual value, plus 1 minus alpha times the forecasted value. Even this will should lead you to the same 278.827, right? The finding out the forecast error, and based on the forecasting error revising your forecast, and based on that computing the updated value. Instead of that, what you can very well do is you take your forecast value as well as your actual value, give alpha weightage to the actual value and 1 minus alpha weightage to your forecast value, which is what will result in the same equation. Alright, so based on this scenario, I can drag out my levels across. So my levels values are going to be towards this kind of a scenario. So this is the forecast I am getting. This is the actual value, and based on this I am giving a 10% weightage to the actuals and the alpha weightage to the actuals and 1 minus alpha weightage to the forecast, which is resulting in my updated level values. But what we are seeing is in this process, the level value is actually getting upgraded. So this is one more thing that we have to take care of. So this, whatever is the change in the level, we'll give one gamma weightage to that and find out the updated slope value, which is nothing but, here I'll take 278 minus 282. That is the change in the level over this period. I multiply this with gamma, and whatever was the slope in the previous period, I'll add back to it. And because of this, again we keep getting that the value would be either going up or going down. So the slope coefficient is taking care of either the upward movement or the downward movement in our graph. So what we are saying is we are splitting the entire price movement into two aspects. One is the level price, two is the slope coefficient, the slope value. So what we are saying as the current level, in the first period we generally don't have any other data. So we are saying the level price is same as the current price. But what happens in the next period, so I am assuming that the next period value also will be same as the current period value only. But in reality, it has actually become 244.78. And because of that, there is a forecasting error, which is resulting in revising our level estimate. Level estimate is in case there is no upward trend or a downward trend, what is the kind of value. So my level estimate is revised to 278. So if it is revised to 278, there is some kind of a fall. So we are assuming that there is some kind of a drop in the value. So what we are doing is we are pulling out a slope estimate which says, no, now the values are no more flat. They will show a downward trend. So the prediction which we are doing for the next period will take the level parameter as well as the slope parameter, which will try to give us the actual forecasted value. So if we had gone only with the level, we could have forecasted it as 278 only for the next period. But because we are taking the slope parameter also into consideration, we end up forecasting it as 278.44. And in some cases, this number is very significant. Probably we are seeing a difference of 100 or something also attached to this. That is what will create our scenario more and more integrative. Now, the next thing that needs to be more understood from our standpoint is, in most of the cases we are seeing a negative values and then positive values in some cases. Now what are the appropriate values of alpha and gamma? For that again I can take a standard error of the data, which is again based on my actual values and the forecasted values. Right, I can very well take some xmy square xmy2, where the array x will be the B column data and array y will be the E column data. Alright, let's do these two things. and let's divide this entire thing by the count of the E column data. This process we have discussed and we have applied quite comfortably till now, and I do the square root of these entire numbers. This tells that the standard error in this process is 391. Now, as we have done even in the other cases, I have to find out what is that value of alpha and gamma which will bring down my standard error overall. Alright, let's try out now. We'll use solver. We cannot use goal seek in this case because we have two parameters to work out on. So I'm setting this value to be my minimum by changing these two parameters, and adding wise I'm saying each one of these parameters should be less than or equal to 1, and similarly each one of these parameters should be greater than or equal to 0. These are the two constraints I'm trying to add in this scenario. With this as the input I'm trying to solve. Now we know that the standard error when I'm taking alpha is 0.1 10% and gamma is 10% is actually 391.23. Now let's try to solve it. Ask our solver to do the scenario for us, which is coming out that you can better take the alpha to be 1, and in this case it's coming out that your standard error is only 139. In some cases we may observe a completely different situation, whereas in this case it is coming out that we can very well take our alpha to be 1 itself. Alright, here we have made a mistake in the formula. We are taking gamma times the difference in the level, but we have just added the previous slope. I have to actually take 1 minus gamma times the previous slope. Alright, so let's see if I add this and run it. So 1 minus gamma times the previous slope. Let me see if things are improved now. Let me start with 0.1 and 0.1 itself. Right now, if I go ahead with this scenario, let me try reusing the solver again with these as the parameters. Now, yeah, even then it is giving us the same solution. So the standard error is getting minimized at 139 when I take alpha equal to 1. So assuming that there's a slope parameter, I'm not taking any specific value. There is no multiplication that is happening to the slope parameter. If I am directly taking in this example, it is very much coming out that you can take the slope parameter gamma as 0. So whether I'm using the Holt method or the typical first differencing method, it's not causing much of a difference to our forecast, because even the first differencing method in this case was giving a more or less similar forecast itself, 799.85, whereas the Holt method is giving me a forecast of 803.82, because it is directly taking the value of 1 to the previous to the level parameter. The level parameter is obtained as the alpha times the current value minus plus 1 minus alpha times the forecast. So based on that, it is arriving at the alpha value. So when we are trying to simplify it, it's able to come out that you can take the value of alpha as 1 and gamma as 0. Only in that case the standard error is coming out much lower, which is working out to 139.9. You can try out with the other data sets and see in some cases, especially Okay, the place where I may have to look at the Holt method more effectively is even after doing a first differencing, if I'm not able to end up with unbiased kind of or unsmoothened kind of data, and if I still see some kind of an active trend even after taking the first differencing, then it looks like the first differencing method used for smoothing is not very effective. So in that case, I may have to resort to the Holt method for doing this process. So for this example, it's not giving much of a benefit because the slope parameter across is looking like a zero itself. So we don't need. So we should only look at some other data, and based on that, take our appropriate action. Right. So try working on some other data series, and then we can look at if there is some issue in terms of handling that kind of a data. All right. So let's move on to our next topic where we bring in regression also into our time series, because here we have looked at the time series data where our focus was moving average, exponential smoothing of the data, those aspects, but we did not bring in any kind of a regression concept into this. So we'll try to integrate a regression mechanism with the time series mechanism, and then try to derive some effective prediction mechanisms. All right, so that's how we'll move on to our next chapter. If you have any doubts on this, please feel free to ask me. I would be very much willing to clear them off. All right, we'll move on to our next chapter then.